So today we'll be evaluating the convergence of the following series, which is going to be the series from n equals 1 to infinity for negative 1 to the n squared, 2 to the n, all over n factorial. And the point that I want to try to get across in this video is during the ratio test, what it is that you can do with factorials in order to break them down and figure out exactly what it is that you can do to them. And the ratio test is going to be a perfect example for this, and I'm going to show you exactly why throughout the course of this video. So in order to evaluate the convergence of this series, essentially what we're going to do is we're going to use the ratio test, which says take the series and take its limit as n approaches infinity for a sub n plus 1 all over a sub n, where a sub n plus 1 is going to be the subsequent term of your series. So if I were to write this down, a sub n plus 1, oh, my marker's dead. So a sub n is essentially going to be our initial series. So let's go ahead and write that down. A sub n is equal to negative 1 to the n squared times 2 to the n all over n factorial. And essentially what a sub n plus 1 is going to be is the subsequent term in that series. So wherever it is that you see an n, you're going to substitute in n plus 1. So a sub n plus 1 is going to be negative 1 to the, now that we see an n over here, we substitute in n plus 1. Then we have n squared. We can substitute in n plus 1 in brackets. This is very important. N plus 1 squared. And then we have 2 to the n plus 1. All divided by, in the place of this n factorial, we're going to substitute in n plus 1 as well. So this becomes n plus 1 factorial. And the ratio test says that if this limit comes out to less than 1, then the series is going to be absolutely convergent. If it's greater than 1, the series is going to diverge. And if the limit is equal to 1, then it's inconclusive. Oh, wrote that down wrong. That's actually... If the limit is equal to 1, then it's going to be inconclusive. So essentially what we're going to do now is we are going to set up our limit. So we want to take the limit as n approaches infinity for a sub n plus 1, which is going to be this whole mess right over here. So we'll go ahead and write that down. This becomes negative 1 to the n plus 1 times n plus 1 squared times 2 to the n plus 1, all divided by n plus 1 factorial. Then we need to divide it by a sub n, which is our original series. So we are going to be dividing it by this mess, which is going to be negative 1 to the n times n squared times 2 to the n, all divided by n factorial. Now I'm going to have to clear some room over here, because essentially what we're going to do now is we're going to flip this and multiply them in order to cancel out any common terms. Whenever you divide fractions, essentially you can multiply by the reciprocal. So if we want to, also, the ratio test involves an absolute value. So we'll take the absolute value of this entire thing, and negative 1 to the n plus 1, regardless of what n is going to be, if you were to take the absolute value of it, it's going to essentially cancel it out. So we can cross this out right away. So this will disappear from our series. So that's going to make our lives slightly simpler. So now, with what's left over, we will take the limit as n approaches infinity for n plus 1 squared, n plus 1 squared times 2 to the n plus 1 over n plus 1 factorial. And since we're dividing by this, we can also just multiply by its reciprocal, so that's what I'm going to do here. So I will multiply this by n factorial over n squared times 2 to the n. And now we have some common factors that can be cancelled out. We have 2 to the n plus 1 over here and 2 to the n. Whenever it is that we divide things with common bases with different exponents, essentially what you want to do is you want to subtract their exponents. So if you wanted to divide 2 to the n plus 1 by 2 to the n, well, you're essentially doing 2 to the n plus 1 minus n. So what you're going to be left over with is just going to be a 2 to the 1 in the numerator. So we'll rewrite that. This becomes the limit as n approaches infinity for n plus 1 squared times 2, I'll pull that out in front over here, times n factorial, all over n squared times n plus 1 factorial. And one thing that I wanted to demonstrate in this video is how it is that you can break down factorial in order to evaluate the convergence of series. What we can view n plus 1 factorial as in a lot of cases, if not all cases of the ratio test, is n plus 1 factorial can be viewed as n plus 1 times n minus 1 times n minus 2 blah blah blah. And what this is it's going to be n plus 1 times n factorial, because this is just going to keep dropping back and back and back. This is n factorial right over here. So we can substitute that in for our n plus 1 factorial over here. So this becomes the limit as n approaches infinity for 2 times n plus 1 squared times n factorial over n squared times n plus 1 factorial can simply be rewritten as n factorial times n plus 1. So now what we can do is we can cancel out a common factor of n plus 1 in the numerator and the denominator. So this will cancel out with this, and the n factorials will also cancel each other out. So all we're going to be left with is the limit as n approaches infinity for 2 times n plus 1 over n squared. Oh, not n factorial, n squared. So this is going to become n squared in the denominator, and now this is just a basic limit as n approaches infinity. We see that the power down here in the denominator is going to be greater than the power in the numerator, so we can automatically conclude that this limit is going to go to 0. And according to the rules of the ratio test that I had set up at the beginning of this video, the limit is 0, which is less than 1. That means that this series is absolutely convergent. If the limit would have gone to 1, the test would have been inconclusive, and if it would have been greater than 1, then we would have known that the series diverged. And that's about everything I wanted to get across in this video. I will see you in the next one.